So in this question here, I've got a complex number expressed as a fraction. 3 plus 4i over 2 plus 5i. That's our complex number z. And we want to express in the form of z equals a plus bi, rei theta, and r cosine theta plus I sine theta. So with this as a fraction, and we've got complex numbers in the bottom as well as the top, how are we going to get that in the form of z equals a plus bi? Well, we can use something similar to how we do with real analysis. Is when we got square roots or radicals in our denominators, we multiply by the conjugate of that square root, and then we can kind of get the square root out of the bottom. It's kind of rationalising a real number. Complex analysis is a little bit similar with that as well. So what we could do is we could take the complex conjugate of this and then multiply it with the numerator and denominator. So we multiply it by 1 effectively, and then we can try and do something from there. So let's go with that. So I've got 3 plus 4i over 2 plus 5i. And then the complex conjugate would be 2 minus 5i. So the real component stays the same, and the imaginary component, we flip the sign. So we'll have 2 minus 5i over 2 minus 5i. So obviously that just becomes a 1. So now what we're going to do now, as in real analysis, just get the numerator and denominator multiplied out and simplify. Let's see where that takes us. So let's deal with each bit at a time. So 3 2s are 6. 3 times minus 5i minus 15i. 4i times 2 is plus 8i. And then this is where we have to be careful. 4i times minus 5i. 5 4s are 20. With a minus it's minus 20. But I squared is minus 1. So that becomes plus 20. So that's the numerator. We can simplify that, no problem. Do the same again here. So 2 times 2 is 4. This is where good things should happen. Plus 5i times 2 is plus 10i. And plus 2 times minus 5i is minus 10i. Hence, that's how we get rid of our complex component. And then we do 5i times 5i, which is 25i squared, which becomes minus 25. And then this minus becomes a plus, so it becomes plus 25. Okay, so without doing that all the steps, what you can do is you can do 2 squared and then do 5 squared, and that will get you to where you want to be. Right, then we can simplify this. That shouldn't be too much of a problem. 26 and imaginary is minus 7i, and then the denominator is just going to be 29. So now we're straight away there on the first one. So the first one, z equals, just break the fraction apart, 26 over 29 minus 7i over 29. Okay, so now we want to go for these two forms. So we need the radius and the argument. The principal argument is what we're kind of looking for. So radius is kind of the easiest one to start with. So let's look for r. So our radius. So let's 26 and 29. So what we can do is just ignore the 29 for the moment, because I could rewrite this as 1 over 29 and then 26 minus 7i. So let's just concentrate on this at the moment, and then I'll bring the 29 in after that. So the real component is 26. Let's just draw that as a line of 26. The imaginary component is minus 7, so that'll be going down 7. So I just put minus 7 there, but it's actually a 7 length. So we now want to find this length here. Well, that's pretty straightforward with Pythagoras. So that would be square root, so if I just put r equals 26 squared plus, I put it as a minus, so you can see that it's the minus, we're getting the habit of using that. 26 squared and 7 squared, that's 676, plus 49, that's 725. Now, using our surds, we can take a 25 out of that. So square root of 25, and then 725 divided by 25 is 29. So then that just becomes 5 root 29. And now I can bring back in the 29 that we have there. So then I've got 5 root 29 over 29. So that would be our final result. So now we've got the radius, leave that as our z. So r equals 5 root 29 over 29. Okay. Now what we got? So we now need to find the argument. So we can see here, if that's our origin, then our principal argument here, theta, is going to be a negative value. So to do that, theta equals the inverse tangent of our imaginary component over our real component, so it's minus 7 over 26. Okay, so that's theta. So we've got theta and our radius. So now what we can do is we can set up this component. So now z equals, radius is this, 5 root 29 over 29, e to the I, and then theta, well, as this is obviously principal argument, so if I do this subscript p for the principal value of theta, that has to be in the range of values of minus pi to pi inclusive. This will fall into that because to go around here, we'd have to be somewhere or approaching pi over 2, or minus pi over 2, or pi over 2 in this direction. So e to the I, and then we got this one here. So that's going to give us a long reoccurring kind of decimal. So I'm just going to write that as inverse tangent minus 7 over 26. So I could leave it in that form, and then the calculator will throw out the correct result for that. So now I need to deal with this one. So let's write that one up. So now give ourselves a bit more space. So let's just box this one off because that's the result finished. That's the way I want to present that one. And then now this one. So z equals r, which is 5 root 29 over 29. And then cosine of theta, which is inverse tangent, minus 7 over 26. Let's just put that in a bracket. And then plus I sine inverse tangent, let's do it in a bracket again, and then minus 7 over 26. Okay, now that would be fine in that kind of format, but I can just distribute some minus signs and get this without this awkward looking input for the cosine. So z equals 5 root 29 over 29. Now I can bring this minus sign out of that and have minus tangent of 7/26. And if I've got cosine minus something, I can then eliminate that because the cosine plus or minus for the input will be the same for the positive. So then I've got cosine inverse tangent, and then just put that one in the bracket this time, 7 over 26. And then this one here, I can bring the minus outside of the tangent to leave positive 7 over 26. But I've got minus input for sine, I can then bring the minus outside. So then I've got minus I sine inverse tangent of 7 over 26. And then that would complete that one. That's how I would present my answer for that one. Okay.